Now we have to try to match the Ekman currents, Ekman transport to the Sverdrup circulation, Sverdrup balance, Sverdrup transports. And before that, let's see why the total integrated Ekman transport is orthogonal to the surface wind. These are the expressions that we saw. Peter makes somewhat of a heuristic argument. So he takes this example where the winds are westerlies, and in this case winds are moving faster than the ocean, than the Earth, so they're called supposed to be in super rotation. So if you move faster than Earth, that's called super rotation. When this happens, if you use your Coriolis, then Coriolis is going to tilt the ocean that's being dragged in this direction by the winds to the right. So let's say here we are across the equator, so you are going to have the Ekman flux coming to the right in the northern hemisphere and to the left in the southern hemisphere. So you are going to converge mass, and you're going to sink it or downwell it, which is going to increase the mass and create this bulge in the sea surface. And his argument is that this increased inertial mass inertia of the ocean because of increased mass leads to conservation of angular momentum. So the atmosphere is giving angular momentum to the ocean, and ocean is increasing its mass because of this convergence and acquiring the angular momentum. Okay, if you have the winds going the other way, then you have divergence, so there is a loss of mass. So in this case, because the winds are going against Earth's rotation, ocean is imparting angular momentum to the atmosphere. So ocean is losing the inertia and imparting angular momentum to the atmosphere, so that the total angular momentum is conserved. I don't know why this is needed, but nonetheless. In other words, he's saying to explain why total integrated Ekman transport is orthogonal to the surface wind, you can use the conservation of angular momentum as the reason why the transport has to be normal or orthogonal to the winds. Ekman transport has to be orthogonal to the winds for angular momentum conservation reasons. Take it. Okay, let's now try to combine the Sverdrup and the Ekman calculations to look at induced geostrophic currents. Starting with our equations, the full set here almost, hydrostatic for the vertical, continuity equation, and the zonal momentum equations, or equations of motion. Let's assume a simple balance again, geostrophic balance, where in the x direction you have minus f times Vg, where Vg is the geostrophic current being balanced by the horizontal pressure gradient in the zonal direction, and similarly in the meridional direction you have f times Ug equals minus 1 over rho 0 dp dy. You should get used to this by now, because Coriolis pushes to the right in the northern hemisphere and to the left in the southern hemisphere. Zonal pressure gradient is going to give you a meridional geostrophic current, and a meridional pressure gradient is going to give you a zonal geostrophic current, right? You can differentiate this with respect to y and this with respect to x, and add them. These will cancel out, dp dx dy dp dy dx, and you will end up with f times dug dx plus dvg dy. Remember the subscripts here, geostrophic currents, plus beta, which is df dy times vg equal to 0. Okay, this is kind of an important relation, even though it looks very simple. We can again integrate that in the vertical, integrate this in the vertical. So we are going to go beta times v bar g, which is the integrated meridional transport now. On the other side you have going from minus d0, depth of no motion, to minus ze. What is minus ze? It is the bottom of the Ekman layer. So we are looking at the interior. This is why we called it the induced geostrophic flow. Friction and wind stress are generating Ekman currents, Ekman layer, and Ekman pumping into the interior below the Ekman layer. The interior is quiescent, low Rossby number, steady flow, so we can go for geostrophic balance. So that gives us dug dx plus dvg dy integrated in over depth. So in this case now v bar g is of course the integral. W is we at ze. That's the Ekman pumping coming in from the top, wind stress curl giving you we, and at that's at ze, and at the level of no motion at some depth, which is not very well defined obviously, we assume that W is 0. That's where the pressure gradient is 0, geostrophic currents are 0, and there is no vertical motion as well. So that basically gives us beta v bar g, which is the meridional transport, equals minus fwe. So Ekman pumping at the top of the interior, at the bottom of the Ekman layer, is inducing meridional transport. Okay, this is the balance we are getting here. So writing again the Ekman equations, balancing Coriolis with the wind stress, du bar e dx, so d dx d dy. Oops, did he make a mistake here? Yes, he did. So this is another error. So it should be x and y is 1 over rho 0 d dx of tau y over f. Okay, we have taken f is independent of x and y, so we can take them inside, minus d dy of tau x over f. So this should be y. I don't know why there are so many errors. Nonetheless, combining those, we get beta v bar g equals f over rho 0 d dx of tau y over f minus d dy of tau x over f. This is just another form of what we looked at before. Before we didn't say, when we did straight balance, we didn't say where we integrate it to. We just said we went to the surface and set w equals 0. Now we are integrating in the interior below the Ekman layer, but the Ekman layer is giving us Ekman pumping through the wind stress relation, the wind stress curl. Okay, so beta v bar in this case then it becomes 1 over rho 0 minus d0 to the surface. Okay, instead of minus ze, we are going all the way to the surface. We had this before, del square tau y or del x del z minus del square tau x or del y del z, and we just got this relation for the interior where we are balancing the horizontal divergence term with the meridional term multiplied by df dy. Just simple manipulations. There is no great problem here. You can just follow it. Writing beta v bar now as a sum of Ekman plus geostrophic currents, we can relate that to 1 over rho 0 of this wind stress curl, d tau y dx minus d tau x dy. So we're just manipulating simple things. And now we can write meridional transport as geostrophic interior plus the Ekman transport, and the geostrophic interior transport can be written as f over beta curl of tau over f. Tau here is of course the vector tau xi plus tau yj. Okay, this is the induced geostrophic transport. So beta Vg is again minus FWE, Ekman pumping, rewriting the expression beta Vg, and WE is minus 1 over rho 0 curl of tau over F. That is, this is WE. So WE is giving us induced geostrophic currents. We will look at the Ekman pumping in a minute, but remember it has tau x over F again. So as you approach the equator, F is going to be singularity. So we are going to not compute Ekman pumping at the equator, but it's valid slightly off the equator where F is small but not 0.